So we're going to talk about inductive and deductive reasoning. So inductive reasoning is the process of drawing a general conclusion by observing a pattern in specific instances. The conclusion is called a hypothesis or conjecture. So a specific observation goes to a general conclusion. It might be true, but it's not guaranteed. So looking at prime numbers, we can see that they can be divided evenly only by itself and 1. So here are some examples of the prime numbers up through 100. So 1 is not a prime number, nor is it not a prime number. It is it's a special case because it is just 1. It's not a prime number, and it's also not a compound number. So it is just 1. But the rest of these are prime. So looking at Box Conjecture, in 1742, Christian Goldbach made the conjecture that he could write every even integer greater than 2 as the sum of 2 prime, not necessarily different numbers. Illustrate Goldbach's conjecture by expressing 20 and 48 as the sum of 2 prime numbers. So we've got the prime numbers listed there. What we want to do is look at the number 20 and write 20 using 2 of those prime numbers up there. So you have to kind of look at the, let me write example 1 here. Look at the numbers. So the first one we're looking at is number 20. And if we look at 20, I need to rewrite 20 using 2 of those numbers. So if I kind of start at the beginning and I look at the number 2, 20 minus 2 would be 18. Well, 18 is not on my list of primes, so I can't use 2. If I use 3, well, 20 minus 3 would be 17. Oh, 17 is also a prime number, so I could use 3 plus 17. Well, that equals 20, and that's 2 prime numbers. If I go to 5, and you only have to write 1, but I want to show you, you could continue on. 20 minus 5 would get me 15. Well, 15 is not a prime number. What about 7? 7 plus 13 would get me 20. So 7 plus 13 is equal to 20. I couldn't use 11 either because 20 minus 11 would get you 9, and 9 is not a prime number. But that's how you can kind of work that out. All right, let's look at 48. So 48, 2 won't work because it's when they're even numbers. 2 is not going to work. You're still going to get an even number, and any even numbers beyond 2 are not prime. If I do 3, 48 minus 3 would be 45. Well, 45 is not a prime number. 5, 48 minus 5 would get me 43. Oh, 43 is a prime number. So I could write it as 5 plus 43. Another example, we could have, let's say, try 7. 48 minus 7 would be 41. So 7 plus 41. And then you could continue on to see if another prime number will work if you have any other cases. But when you're, like, if this was a test question you need, or homework, you only need to give me one example. I'm just showing you, you don't all have to have the exact same example. There could be different ones. All right, so, and understand, no one's been able to prove Goldbach's conjecture. Many believe it to be true based on inductive reasoning because we're looking at specific observations going to general conclusions. So it's not proven to be true, but that is his conjecture that that is what is the case. Now, there's a warning that inductive reasoning can lead to false conclusions. So in other words, something is true that is not. So be careful about that. All right, so let's look at example 2. So for example 2, we want to consider this set of numbers. So we have 3, 8, 13, and 18. So what is most likely to be the next number? So if we're looking at this, what is most likely to be the next number? So we have to figure out basically what the pattern is. So if we're looking at 3 to 8 to 13 to 18, our pattern is what? Well, 8 minus 3 would be 5. So 3 plus 5 is 8. 8 plus 5, oh, that's 13. 13 plus 5 is 18. So if I add 5 to that, what would be my next number? 23. And the pattern is plus 5. So the y of that would be that there is a pattern of plus 5. So we could continue to find the next number. Now, if we wanted to do this in a complete sentence, so if we wanted to write this as a sentence, we could say that the next number is found by adding 5 to the previous number. So if I'm trying to write a complete sentence, I'm just going to restate what I know using words. All right, let's look at example 3. So we want to identify the next number in the sequence. So if we have 1, 1, 2, 3, 5, and we have a blank. What is the next number in the sequence? Well, this one isn't, between 1 and 1 there is no difference. So it's not like it was up here with the 3 and the 8. So 1 and 1, and then we went to 2. Well, 1 times 2 is 2. But 2 times 2 would not be 3, so that doesn't work. And let's see. 1 times 1 is 1. 1 times 2 is 3. 2 times 3 is, no. Well, let's look at it again. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 would be 8. So 8 would be our number. This is actually called the Fibonacci sequence. So what we can do for a sentence for this is the next number is found by adding the previous two numbers. So by adding the previous two numbers, we end up with the next number. All right. So let's go look at example 4. Example 4 is back on our handout. And we want to divide a circle into regions by selecting points on its circumference and drawing the line segments from each point. So we can draw 1. If I put 2 points and draw a line. So this has 1 point, 1 region, 2 points, 2 regions, 3 points, and I draw the lines. I end up with 3 points plus, and I get 4 regions. So I have 1, 2, 3, and 4 regions. If I put on 4 points, I end up with 8 regions. 1, 2, 3, 4, 5, 6, 7, and 8. So we're going to use inductive reasoning to find the greatest number of regions we could get if we had 6 points on the edge of the circle. Now sometimes inductive reasoning from specific examples is all we have to make with sales, attendance, and behavior. So what I did here for time purposes, I drew out, this is for 5. So for 5 points, I wanted to see how many regions we would get. And if we count all of these, with 5 points, I get 16 regions. So understand that 1 point, 1 region, 2 points, 2 regions, 3 points, 4 regions, 4 points, 8 regions. So let's write that out again. Let's write that down on paper so we can kind of see how the numbers are going. Because we want to know how many, we're going to end up with 6. So let's do a conjecture. This will be example 4. And we're going to do a conjecture that, so we had 1 point, we had 1 region. For 2 points, we had 2 regions. For 3 points, we had 4 regions. For 4 points, we have 8 regions. So we would have 5 points and we would have 6 points, because that's what we're looking at. So what happens to our numbers? Well, if you look at the pattern of numbers, they're being doubled, right? So 1 times 2 would be 2, 2 times 2 would be 4, 4 times 2 would be 8. So we would expect in 5 that we should get 8 times 2 would be 16 regions, and 16 times 2, we are expecting that we should get 32 regions for 6 points. So that's our conjecture, is that's what's going to happen. We're going to have 32 regions. Alrighty, so I drew out the 5. And when I drew out the 5, let me move my camera just a little bit here. So when I drew out the 5 points, I got 1, 2, 3, 4, 5 points. If you count all of the regions, you end up with 16 regions. So I have 16 regions on this one. So you could count them out. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 regions. Then I drew out the 6. So if we all drew out 6 points, we've got 1, 2, 3, 4, 5, 6. When I count them all out, and you have to be careful, there is one that ends up here. So when you're drawing yours, be aware that you should have one in the middle. When I count these, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and 31. I end up with only 31 regions. So, what we're finding is our conjecture, this is actually false. We're only going to get 31. This one is true. We get 16 regions. Here we're only going to get 31. So we were looking at specific examples and then drawing a general statement. But these sometimes can be false, so be aware of that. Okay, so let's go talk about deductive reasoning. So deductive reasoning tells us that use accepted facts and general principles to arrive at a specific conclusion. So general statement gets us a specific conclusion. Example, class is required to have a syllabus. So if all classes are required to a syllabus, we can conclude that our Math 1332 class has a syllabus. That's one way to look at that. So I want to talk a little bit about inductive and deductive just to make it a little more clear. So here we have, I found this on the web. So just so you know, I didn't create it. We have deduction versus induction. And we have Aristotle versus Sherlock. So induction was the first one we talked about. And so we're looking at taking it from observations, noticing a pattern, creating a hypothesis, which is a conjecture, and then taking that to a theory. So on the last problem, we used an observation of the numbers were doubling. We looked at the pattern to see that. We went to a hypothesis and then looked to see if we could take it to a theory. It was false on that one, but it was true on some of the other ones that we looked at. Now for deduction, you're going to start with a theory, then go to a hypothesis, do some observations, and then confirm if it is true. And that's something that Aristotle would have looked at. He would have looked at theory and then gone down to some confirmations. So that might make it a little bit easier. So here is some other things on deduction. So deduction moves from idea to observation, while induction moves from observation to idea. So there's where it's kind of going back. Are they taking an idea and then looking at how it happens, or do they look at how it happens and take it to an idea? Deduction moves from general to more specific, while induction moves from specific to more general. Deductive arguments have unassailable conclusions, assuming all the premises are true, but inductive arguments simply have some measure of probability that the argument is true, based on the strength of the argument and the evidence to support it. So for deductive reasoning, all men are mortal. Okay, Harold is a man, therefore Harold is mortal. So we're looking at going from a theory that everybody's mortal and taking it all the way down to the confirmation. Well, yes, he is. He is mortal. Now, so the third sentence is absolutely true because if the first sentences are true, the first two. I have a bag of many coins. I've pulled out 10 at random, and they've all been pennies. Therefore, this is probably a bag full of pennies. So, if you have a bag of coins and you pulled out 10 at random and they've all been pennies, you're making a conclusion that it's a whole bag full of pennies. But is that necessarily true? So, not sure. I mean, you could have one nickel down in the bottom, but you're making a conclusion or you're noticing some ideas of what's happening, and then you are taking it to that statement. So you're looking at the fact that specifically I've observed the coins coming out, so I'm taking it to a general statement. Okay? So just this could be true, but there could be an instance where it's not. But that's kind of the difference between them. Alrighty, so let's go look at some examples with deductive reasoning. So we're going to solve a Ken-Ken puzzle. Now, I had never done Ken-Ken puzzles until I started teaching this class, and they're actually kind of cool. So consider the grid of numbers. The rows are going to be labeled A through D. We're doing a 4 by 4. Columns are 1 to 4. You're going to fill in the smaller squares called cells using numbers 1, 2, 3, and 4. However, no number can be repeated in any row or column. The small numbers in the corners of some cells give instructions as to what must appear in the colored regions. So this is what it looks like on your handout, and I've replicated it for the ease of here because I wasn't sure how well it would show up in the video. So this is more of what we're looking at. So we've got our A through D and our 1 through 4. Now, what it was talking about is these little numbers up here tell us what's happening. So if it's just a number, then that means that's the total sum of that number. You can see that in the red and the orange, that we have a 1 here. These are the numbers we're given, and that's a 1. This is a 3, and the total is 3. Now you can see pluses and minuses. What that means is when these two are added, they will total 6. When these three are added, they will total 6. when these two, they were, you will be subtraction, and that subtraction will equal the amount of 1. And then if it is here, this one, the difference between them will be 2. Okay, so the sum will be 10, the difference will be 1, the difference will be 2. All right. And I realize we skipped number 5. We'll come back and do it since we've already started on the kin-kin puzzle. So let me double check. Yes, we'll come back and look at it. All right. I just saw it next on the thing and I wasn't paying attention to the numbers. So this is actually example 6, and we'll come back and do example 5. It doesn't matter. All right, so as we're adding these, we have to kind of figure out where to start. So we're given a few things. What we need to figure out is what we can come up with. So in row D, we only have 2 numbers here. We can see we've already got a few things told to us. This number can't be a 3. We know that there's only a couple of choices here. If you notice, there's a 1 here, a 1 in this column, a 1 in this column. That means this column has to have a 1. See that? There's a 1, and a 1. So these columns and these rows already have a 1. So the only place a 1 can go is here. A 1 has to be there. So if this has to be a 1, and the difference between these have to be 2, then that tells us that this will have to be 3. Because 3 minus 2 will get us to 1. Now, in this row, we have to have 1 through 4. So that tells me I have 1, I have 3 and 4. This will have to be a 2. So now that I have those numbers, let's see what else we can figure out. Alrighty, so here we know that in this row here, we have 1 and 3, we need 2 and 4 to finish out this row. Well, this row already, or this column already has a 2, so this can't be a 2. This column already has a 4, so it can't be a 4. So that means this has to be a 4, and let's double check that. The sum has to be 10, so 4 plus 2 would be 6, plus 4, that would be 10. So it's kind of a little bit like kin-kin and Sudoku. And then this would be 2, because I have 1, 2, 3, and 4. Well, this tells me this should be a 3, 1, 2, and 4. This should be a 3. Well, 3 minus 2, that is a difference of 1. So that'll be my 3 right there. Now, this row here, this column here, we have 1, 2, this should be a 3, and then here we have 4. So if I put a 3 here, and I have to total 6 on the green, 1 plus 3 is 4, plus 2 would get me 6. So that totals to be 6, so that checks. Here I have 1, 2, 3. I need a 4. Well, the 2 white ones have to have a difference of 1. So 4 minus 1, oh, that would be 3. So I can place a 4 there. So now I've got 4, 1, and a 3. So I need a 2 right here to finish out my row. So that would be 2. And that means this would have to be to total 6. When I add them, 2 plus 4 is 6. And I have 1, 2, 3, and 4 here. So I was able to do this using some deductive reasoning to solve this and figuring out what's going on. All right, so this was example 6. Let's go back and do example 5, and then we'll go do another type of kin-kin puzzle. Sorry about that kind of flip there. All right, so let's look at example 5. So we're going to do a divisibility test. For 9. Now this would be inductive. So we're going to consider the following numbers and verify if they are evenly divisible by 9 or not. Then we'll add the digits of each number and see if we see a pattern and make a conjecture. So if we're looking at part A, we're looking at 72 divided by 9 is equal to 8. So then we're going to say that if we add these two together, 7 plus 2, well, that equals 9. All right, let's look at B. If we take 491 and divide it by 9, we will find that we get 54.56. If we take the numbers 4 plus 9 plus 1, we actually get 14. All right, part C. If we take 963 divided by 9, we'll get 107. We're using a calculator for that part. So let's take 9 plus 6 plus 3 is equal to 18. So we're taking the number, we're dividing by 9 and adding up the digits. All right, let's look at D. We have 19856 divided by 9. We get 2206.22. We take 1 plus 9 plus 8 plus 5 plus 6 gets us 29. Part E, if we have 45307 divided by 9, we get 483.4.11. Well, let's add those. 4 plus 5 plus 3 plus 0 plus 7 equals 19. So my question for you, what are you observing? We're seeing that some work, we get a whole number, and some don't. What's the difference in what we're doing? Well, if you look at the numbers that evenly divided by 9, the number itself, the digits in it, add up to a number that's divisible by 9. So 7 plus 2 is 9. 9 divided by 9 would be 1. It would work. On this one, 9 plus 6 plus 3 got us 18. 18 divided by 9 would be 2. So it divides evenly by 9. But if we look over here where it didn't divide by 9, when we add it, 14 is not divisible by 9. We would get a decimal, not a whole number. Same thing happened here. 29 divided by 9, we would also get a decimal answer. And here we would get 19 divided by 9. It would also be a decimal answer. But if we take that sum and divide by 9, we get 1. Divide by 9, we get 2. If we divide this by 9, we're not going to get a whole number, or this one or that one, and then it doesn't work. So the rule has become, or our conjecture is, that in order for 9 to divide evenly into a number, 9 must divide the sum of the digits of the number. So I can tell you that this one would be like 2.11. Divided by 9, this would be 1.56, just to clarify for you. Divide by 9, this would be equal to 3.22. So let's look at another one that's really big. Let's do example F. So if we do example F, let's see if we think it will divide by 9. So 7538463 divided by 9. Well, if we divide that using the calculator, we get 837607. So we would think that the sum of these numbers will divide by 9. So let's see. We have 7 plus 5 plus 3 plus 8 plus 4 plus 6 plus 3 will equal 36 when we add them together. Does it divide by 9? Well, divided by 9, that'll be 4. So no matter if it's a big or small number, if the sum of the numbers divides by 9, it will equal 4. So that's kind of cool that that has become a way to see if a number is divisible by 9. There are other numbers that you can do that with, and so it's really kind of cool that you can see how things work. All right, so the next one that we are going to look at, we're going now to example 7. And again, I'm so sorry I went in the wrong order. It's on our handout. We're going to use deductive reasoning to solve a puzzle. So 4 students, Alex, Noah, and Winnie, participate in different college activities. You want to use the following clues to determine the activity of each student. So Winnie lives in the same apartment complex as the musician and theater participant. The musician and Noah were friends in high school. Carmela has a heavier course load than the basketball player, but fewer credits than the theater participant. And Noah, who has the fewest credits, is not on the debate team. Well, let's go see what we can figure out that's happening with this. So we're going to draw a chart. So you'll see me actually kind of draw one out. We're going to do something like a ken-ken here. So I've got 4 things on each part here again. So I'll split it in half this way and this way. So if you're trying to draw one out, if you just keep dividing it the halves by halves, you can kind of get somewhat even squares. All right, so we figured out we have 4 people that are involved in our puzzle. We have Alex, Noah, and Winnie that they told us about, and we also have Carmela. So we have Alex, Carmela, Noah, and Winnie. We'll put them in alphabetical order. And then we know that they are on 4 activities: debate team, basketball, orchestra, or theater. So we have debate, basketball, orchestra, and theater. All right, so now we've got to use what we know to figure this out. So, use the clues to determine the activity of each student. So it says that Winnie lives in the same apartment complex as the musician and theater participant. Well, that tells us that Winnie is not in orchestra and she is not in the theater. So as we're reading this, this tells us what Winnie isn't. She's not a musician or theater. That tells us that Winnie has to be in basketball or debate. But it hasn't told us something yet. All right, the musician and Noah were friends in high school. Carmela has a heavier course load than the basketball team, or the basketball player, sorry, but fewer credits in theater. So that tells us Carmela. Well, we know that Noah is, so let's go back and kind of start from again. So let's see what we can kind of determine. Because we can read these over and over, but if you don't start making some markings on your chart, you won't know the difference. So Winnie lives in the same apartment complex as the musician and the theater. So we know that she is not the musician. And I'm going to put a -1 so we know that it's because of clue 1. She is not these. All right? So we know she's not those. The musician and Noah were friends in high school. So that tells me that Noah is not a musician because of clue 2. Carmela has a heavier course load than the basketball player, but fewer credits than the theater. So Carmela, not the basketball player, and not the theater person. Noah, who has the fewest credits, is not on the debate team. So we know that he is not on the debate team. And we know that he has the fewest credits. Well, we already know he has the fewest credits. He's not on the debate. And we know that according to Carmela, she had a heavier course load than basketball, but fewer credits than theater. Well, if she had fewer credits than theater, but Noah had the fewest credits, he also cannot be a theater participant. So that tells us that Noah is going to be the basketball player. Well, if Noah is the basketball player, then that means that Winnie cannot be the basketball player, and we know that Alex cannot be the basketball player. So that tells us that Winnie is the debate member, which means that Carmela and Alex cannot be the debate member. So that tells us that Carmela will then be the orchestra, which means that Alex cannot be, but Alex is the theater player. I find it helpful to put the number of the clue that helped you out, because that way when you're looking back on it, you'll know that these came from clues and these came from your deductive reasoning. Because we figured out Noah by the clues, and then we could figure out Winnie, which allowed us to figure out Carmela, and all of those allowed us to figure out who Alex was.